Thank you, Judd. Thank you so much. I don't know if I've ever had such a fabulous introduction before. One of the things I love about the Haskell community is the close connection between academics and industry folks at conferences like Lambda Jam and ICFP. And so I'm very, very delighted to be speaking here today. So let me just jump into what I'm talking about today. So today, so I'm going to talk about strongly typed system F and GHC. And I want everybody to think about this as a challenge problem. As the idea of this talk kind of started with a challenge of, can you do this in your favorite functional programming language, right? And what is this, right? So this is, we're going to represent a data type for the abstract syntax of some other programming language, right? And in this case, the object language that we're going to be representing is system F, but we're not just going to use any data structure to represent system F. We want to have a strongly typed data structure. But what I mean by that is I want my data structure to be so constrained that it only can represent well-typed terms. Now, what I'm going to talk about today is I'm going to go over a solution that I have developed to this challenge problem in the Haskell programming language. And before I go any further, I want to point out that if you get excited or impatient and want to see the answer, I've put up all of the code plus more extended elaboration, much more than I'm going to be able to cover today at this GitHub repo that you see at the bottom of the slide. And I'll repeat it again at the end of the talk. But everything that you see today will be accessible to you to play around with afterwards. Okay, so let's talk a little bit more about this adventure that we're going to go on today. Oh, and I should also mention, I put in a lot of pictures of dragons in this talk. To me, dragons kind of represent a challenge. When I was a kid, my favorite book was about this princess who went out and decided to be a dragon killer. So we have some dragons that we're going to go out and hunt in our adventure. So how are we going to chart that adventure? What are we going to see today? So I'm going to start with just a simpler version, right? We're not going to do system F all at once. We're going to start with a smaller dragon, which is the simply typed lambda calculus. And we're going to use this technique called de Bruijn indices to represent the variables of this simpler language. And as we go through and work out how we can represent this small lambda calculus, what we're going to develop in the process is a very general interface for substitution that would be the seed of a library that you could use to implement a more general substitution library for implementing programming languages. Something like, so in the past, I implemented a language called Unbound, and EdCommit implemented a language called Bound. They're both very much related to what we're just going to see just a very small model of at the end of this first section. The second thing we're going to do is then we're going to extend it to a strongly typed representation. So the first one is just going to be a standard lambda calculus representation talking about how to do the de Bruijn indices. The second one, we're going to do a strongly typed version. And in that strongly typed version, we're going to do exactly the same thing, but this time the types are going to tell us more. This time, the types are going to prove to us that when we do a substitution with the same code for the substitution, but when we do that substitution, we're going to find out that we haven't screwed up the types in our type system. And then the third part of the talk, we're going to take these two ideas that we start of doing it first with an untyped representation and then with a typed representation. We're going to take those two ideas, mix them together, and use that to build up a representation of system F. Use it to build up a language that has polymorphism. Right, and we're going to need to draw on a particular library that supports dependently typed programming, the singletons library. This is a library that my student Richard Eisenberg has developed specifically for dependently typed programming in Haskell. So we'll see a short example of what that can get you. Now I'm going to warn you right up front, not all of the dragons will be slain in this talk. There is no fairy tale ending, but we will have some fun along the way. So with that, let me just dive in, and we'll start with our simply typed lambda calculus. But before that, before we go any further, before we go on any kind of quest, maybe we should go to the library and look for some ancient documents that can be a guide for our way. And in fact, before I need to acknowledge that I found this one ancient document about how to do strongly typed term representations in a different language, in the language of the Coq proof assistant. And this was a very strong inspiration for the Haskell development that I'm going to show you today. Looking at dependently typed programs written in other languages has been a hobby for me, and trying to translate them to Haskell to see what they look like in Haskell. I find that very fun, and this is yet another example in that vein. Okay, so simply typed lambda calculus, right? So this is, I pulled these typing rules from Wikipedia. This is a very standard way of capturing the essence of a typed programming language. So let me see, I should have a laser pointer. I hope it's visible. So you can see here, there is so we have 4 rules, right? So we have variables, we have some kind of constants. It doesn't really matter what kind of constants. In my example, we'll have constant integers. We'll have functions with function types, and then we have applications where we can apply functions. So this is the language that we want to implement, that we want to represent in Haskell. And here's a data structure that we can use for representing this language. So we need some data structure to talk about the types of this language. It's a simply type. So we have our base type is some int type, and then we have arrow types. And then we have our 4 different expression forms for constant integers, variables, functions, and applications. And the thing to notice about variables is I'm representing variables with this type that I would call IDX. And that IDX, it stands for index, because I'm going to be using de Bruijn indices to represent variables, where we're going to count enclosing lambda binders. And I'll show you an example of this. But the key idea is that we don't have any variable names anywhere. We just need to count. If we want to know what a variable resolves to, we just need to count how many lambda binders it's nested inside. And to make sure that we don't confuse our integer constants with our variables, I'm using a different type to keep those 2 kinds of numbers separate from each other. Oh, and another thing is, if you have managed to find the GitHub repo, or if you see my slides, which will all be in the GitHub repo afterwards, each slide has a little reference to which file the code is coming from, if you want to follow along. Okay, so let's look at an example. So here's a lambda term that we might want to represent, right? And so you could see we bind a variable x, we apply it to a function, which binds a variable y, applies the same x to y again. And I've colored it so that you can kind of match it up with its representation. So with the de Bruijn indices, this x goes out to the 0th lambda. So there's no lambdas in between this x and where it's bound. So we're going to use 0 to represent that one. This x, the green one over here, we're using 1 because we have to jump over this 1 lambda before we find the lambda where it is bound. So we just need to count to be able to figure out which particular index to represent each variable. Right, like similarly over here, this 0 refers to y, which is bound here. So even though we have a 0 up here and a 0 down here, they're in different parts of the term. They're nested inside different lambdas, and so they refer to different variables. Now, the nice thing about this representation is that variable names don't matter using this representation, right? So if we want to know whether lambda x.x is equal to lambda y.y, well, they're going to be represented with exactly the same term. So they're going to trivially be equal to each other. And that's actually very convenient because we don't want to distinguish those 2 functions from each other. We want to think of them as the same function. Okay, so let's look at an example of an operation that we might want to use, like just a simple function that we might want to use with this data structure, with these terms. So what I'm going to implement is a simple evaluator for lambda calculus terms. And so each of those expressions I want to turn into something of this data type. I want to evaluate an expression into a value. And my values are either going to be integer values or functions. And we can do that with an interpreter that kind of looks like this, right? So we're going to evaluate an expression to a value. If it's an integer expression, then it's directly an integer value. If it's a variable, oh, I forgot to tell you, I want to only evaluate closed terms. So it's a variable, I don't want to see it. I want this to be an error case. If it's a lambda expression, then that's directly a lambda value. If it's an application, I have to do a little bit of work, right? So here, if it's an application, I have to first evaluate the function part of the application. And if that function happens to be an integer, then this is where I'm going to get a type error in my simply typed lambda calculus. You can't apply an integer to something, to an argument. But hopefully, if I get a lambda value, then that's something I can apply. And here's where the point where I have to do something, I have to do some substitution. Here's the point where I want to keep evaluating the body of this lambda expression, but this is a lambda, this is a function, it's got an argument. I want to fill in that argument with I want to fill in that parameter with its argument. So I want to substitute E2 for whatever variable 0 is in E1 prime. Right, so here I have to define what substitution is to be able to finish this evaluator. Okay, so here's where things get a little bit tricky, right? We have to implement substitution for this representation of lambda terms where we're using indices to represent variables, right? And so what happens? What does it mean to do a substitution? When we want to substitute E2 for variable 0 in E1. How might we implement that operation? Now, let's just think about maybe some simple cases first, and then we'll go a little bit more general, right? So imagine the body of our lambda expression that we're substituting into E1 doesn't have any nested lambdas inside of it, right? So this is the simplest case we can think of, right? So if there are no lambdas inside, right, then we just need to find all the var zeros in there and replace them with E2. But what if there was a situation where E1 wasn't closed? There were some free variables around. Now, maybe in this implementation with eval, I said I wanted to only do it for closed terms, but I want substitution to be general. I want it to apply to, I'll use it in other situations as well. So if E1 is not closed, I also have to do this other thing while I'm substituting. I have to decrement all other variables. Sorry, I hope you can't, I don't know if you can hear my cat. She just came in. Hopefully she'll keep it down. Okay, so if E1 is not closed, it has some other free variables. We're going to be removing the binder around it, right? We're going to decrease their binding level, so we need to decrement them as well. Okay, so that was the simple case, right? But what if there were binders in E1? What do we have to do there? Well, yes, Freya. Here she is. She gets to be on the video. If there are variables, if there are binders, right, and the variable that was 0 is under a binder, then we need to start looking for 1, right? So if there's one binder, we have to look for var 1. Going even more general, maybe there are in binders, so we have to keep track of how many binders we're going down, and we have to look for in. And at the same time, we still have to worry about free variables in E1 and decrementing them. And one more situation, if E1 has binders, we're putting E2 underneath those binders, and we don't want to capture any free variables in E2. And so at the same time as we're decrementing variables in E1, we also have to increment variables in E2 to make sure that they don't get captured. Now, this is about the point where thinking about substitution with de Bruijn indices my head starts to explode, right? I'm like, do I really have to think about all these different cases every time I want to implement substitution for my little language, right? Is there a way I can encapsulate this reasoning so that I only have to figure it out once and I don't have to keep re-implementing the same thing over and over again? Right. So there's a little drag in there. That's our challenge. Can we encapsulate this reasoning so we don't have to do all of this counting the binding level, figuring out whether we're decrementing or incrementing? What can we do? So let's try to divide up what we're implementing into two parts: a reusable library, and then the part we need specifically for this particular application, right? So the bottom part, blue, that's specific for the simply typed lambda calculus. This is the substitution function that we have to implement, that it has to be specific to this lambda calculus because it has to do this recursive traversal over the lambda calculus term. So, but maybe we can abstract away what exactly we're doing when we do the substitution. And so what I want to do is I want to introduce this abstract type of an idea of a substitution. And then I want to, that's up in the green box. This is sort of the library. And then I want to have some operations that I can use to define for each of my languages what the substitution operation is for that language. So if you remember before, I wanted to replace 0 with some right-hand side with some E2. So I need a way of creating that single substitution. So there's one constructor for this abstract substitution type. Down here in my implementation, mostly the substitution just crawls over the term. Like if we have an integer, we don't need to do anything for substitution. If we have an application, we just need to substitute into this two subterms of the application. The two places where we have to do something specific are in the variable case. That's where we actually need to look up what the substitution does to that variable. If it's variable 0, we need to get out E2. Maybe it's another variable that we have to shift it a little bit. If it's a lambda, we need to call the substitution recursively, but we're going to transform the substitution using this operation that I'm calling lift. We're going to transform that substitution so that it's appropriate for going under the binder. And this is how I'm going to keep track of that nesting level of my operation. This is abstract, but you can see that it's a very specific, easy to grasp pattern for the definition of the term, and a lot of the complexity is hidden behind what goes on in the implementation of the library. Now, when you're looking at this, you might think, okay, it's not quite a general purpose library because I still am referring to the exp type in the signature of these library functions. So it's not a general library yet. So I need to do one more step to generalize it. Right, so what do I have to do? Well, I have to make the type a little bit more polymorphic. So I add a type parameter to say, I'm doing a substitution for an A, right? So A is going to be a parameter in this example. It will be exp, right? I want to create a substitution for expressions, right? And so my single sub constructor is going to take A's and give me substitutions for A's. Now, what about this apply sub? So when I take a substitution for A's and I get an index, I should get an A back out, right? I'm looking up that index in that substitution. But I need a little bit of extra information from my language to be able to do this generically. And that's what this type class constraint is about. The type class constraint is holding the information from the language that I need, right? So what do I need for apply sub? Well, sometimes when I look up for an index, I need to return, the thing from the right-hand side, but sometimes I need to shift that index down. So I just need to change the index, but make a new variable. So I need to know what the variable constructor is for my language. So one component of that type class is how to create a variable of a particular index. And if I have that, that's going to help me define this apply sub in a general way. Now, lift also has the same constraint. This is the lift, if you remember, was an operation that is going to transform a substitution so that it's appropriate for going under a binder, right? But lift has to do a little bit more, because not only does it have to modify what's going on in the substitution, but it also has to go in everything that's in the right-hand side. We also had to increment those variables while we were decrementing others. We also lift also needs to know what is the substitution operation itself so it can do those decrements. Now, I'm not going to show you how this all works out because I want to get to other parts of the talk, but I want to tell you is that this interface gives us a nice way of capturing exactly what the reusable part is and what part you need to do specific for your language. Now, of course, we could go much more deeply into this. I'm going to stop here. There's more that we can do, and I'd happy to follow up after that. But what I want to show next is how we can use this, if we have this library, how we can use this to get our substitution and finish out our evaluation example, right? And this part, this is almost what we've seen before, right? So in this part, we just need to import the library that defines these operations, and then we have to create an instance of that type class that tells the library, here's what the variable constructor is, and here's how to define the substitution operation in terms of the apply, sub, and lift operations that come from the library. And boom, once we do that, now we have substitution for our particular lambda calculus. And we didn't have to think about shifting or decrementing variables or incrementing variables at all. We just thought about it in terms of looking up substitutions and modifying substitutions as we go under binders. Right, and once we've done that, then I can finally do this last line of my evaluator example, right? So you remember, for evaluating the application of a lambda expression to an argument, we need to create a substitution with the argument and call the substitution function with that new sub in the body. And that is going to work out for us. Okay, so that's the first part. That we did this all with a weakly typed or untyped abstract syntax tree. And what do I mean by that, right? So in this example, you can see that we're not enforcing our expression data type to only represent things that type check and they simply type lambda calculus. We could have things that are type errors, and then we're not enforcing that this evaluator only works for closed terms. What I want to talk about next is how we can modify this data structure and modify the substitution library so that we can rule out these error cases, rule out the second line where we're trying to evaluate an expression with an unbound variable, and rule out this line down here, the next to last line, where rule out applying an integer to an argument, something that would be a type error in our language, right? And so our technique for defining the strongly typed abstract syntax is going to be to use a GADT, to add some type indices to our representation of the lambda calculus term that capture what the type system is, right? So if you just look at the purple, parts, it's the same data type definition that you saw before. But now I have two extra components. I have two extra parameters for this data type definition, right? So the second parameter that I've always used orange for, this is for the type of the expression that I'm representing. So you can see that these integer literals, right? The expression now says I am an expression that is representing something that has the integer type, right? And for lambda expression, I'm going to get something that is an expression that has a function type, right? So we're using that type index to constrain and give us information about the syntax that we're representing. The green part is, that's for the context. That's the typing context. We might have some variables in there, and the green is remembering what the types of those variables are. And that we're going to use this right here. This is a list of types. Our variables are indices. They're natural numbers. They're just indexes into that list. So the type of the variable, we're going to delegate to this auxiliary type here, but all this does is it's going to look up in this list and find out what index in that list this type is. And that's what type that variable will have. In just a sec, I'll show you the definition of what index is. This is both proving that that variable index is in scope, right? You can view this typing context as a scope. So it's going to prove that that variable index is in scope, but it's also going to give us what the type of the variable is in that context. Now, when we have a lambda expression, we are going to be introducing a new variable. And you can see that happen here in the body of the lambda expression. So here in the body of the lambda expression, you can see in the body of the lambda expression, we are taking the typing context and we're adding a new type to it. We're adding the type of the parameter. This is just a normal Haskell cons operator for a list. We're making a bigger list with a new type in the front, and that's recording that index 0 has the type T1, which is the type of the parameter to this function. All right, and then lastly, down here for application, if we have a function that has an arrow type, right, then we better have an argument where the argument's type has to match up with the parameter that the arrow expects. And then the result type of the application has to be the result type of what the function was. Right? So all of these type definitions together are going to constrain our data structure so that we are only going to get simply typed lambda calculus terms, things that type check. All other lambda calculus terms are just not going to, the Haskell type checker is going to rule them out before we even start working with them. Now, in order to finish, to continue our example, right, I promised we would not just represent the terms, but we also need to work with them. And so what I want to do is modify our substitution library so that it also talks about these types. So that when we apply substitutions, if we start with a well-typed expression and apply a substitution to it, we should still have a well-typed expression in the end, right? So the first building block of that is to be able to talk about indices that are references into a list. Right, so if you look closely at this index type, I know there's a lot of text on the screen, but if you look closely at this type, if you squint a lot, you'll see that it's isomorphic to the natural numbers. We have a 0 constructor, that's 0, and we have successor that takes an index and gives us another index. Right, so these are natural numbers, they're just indices. The 0 index is the index to the first position in the list. Right, so this says that T is found at the top of the list, at the 0th position. The successor index says that T is found later in the list. So if we have a list, it's non-empty, and we should know the successor index is going to tell us if we can find T in here, then the successor is going to push it and say, well, we need to go look one more to find out where index T is, right? So this is going to give us a proof that every index is going to be in bounds in this list, and the second component is going to be the type that it's looked up with that index, right? And so this is exactly what we need to be able to represent well-typed variables, variables that are well-typed within some typing context. Now, another thing that I want you to notice about this definition is I want you to look closely and look at the kind of index, right? So I wrote it like this. I put explicitly in Haskell what its kind is. It takes a list of Ks and a K. I want it to be a very generic thing. And so what we say is that index has this polymorphic kind. It doesn't really matter what goes in the list, right? We can index into any kind of list. And we can show that something is found in any kind of list. We don't care what kind of list it is. So we can generalize over those kinds of values, right? And this is good because then we can use index in any situation we want, like, for example, to build expressions. And notice that if we instantiate this K here with tie, we're going to get the type of our indexed expression type. Okay, so let's look at some examples of using that indexed expression type that we just saw. right? So I showed you how we could take the expression type, add 2 parameters to it, and suddenly constrain it so that it only represents well-typed expressions, right? Now I should show you how to work with those well-typed expressions. Now we have to do one more thing. So I want to do this big step evaluator again. You remember we evaluated expressions to values. We need to index our values in the same way that we indexed expressions. I'm not going to show you all the details there so that I can fit it all on the slide. But what it does let me do is give a much more precise type of my evaluator now. Now I can say my evaluator is going to take an expression that has to be closed. And I know this expression has no free variables because the typing context is the empty list, right? And there can't be any variables in a term that type checks with an empty typing context. So I'm going to take an expression that is closed and I'm going to evaluate it and get a closed value. So our type is telling us a lot of information, right? So what does the term look like with those types, right? The great thing is the term looks exactly the same as before. We don't have to change the program that we wrote, even though we've made the types more descriptive, right? So the evaluator for ints is the same. We can comment out this case, and Haskell's coverage checker will know that we don't need this case anymore. We'll be able to tell that this case is impossible. In fact, if I didn't comment it out, Haskell would give me a type error to say this is a redundant case. It's inaccessible because you're not allowed to have a variable in an empty typing context. Lambda's expression works exactly the same as before. Application, we're going to evaluate it. We know this time when we evaluate it, application has to give us this E1 has to have the type of a function type. So we're not going to get an int value out for a function type. So we can comment that out, and Haskell will tell us to do that, right? And so we know we are going to get a lambda expression. And then the code, we want to just be able to write the same code that we wrote before with that substitution. Now we're only going to be able to do that if we can add more types to our substitution library. And before I go a little bit further, I want to tell you I now have 2 cats on my lap. So here's one, and here's the other. They have joined me, and they are keeping me company here. Okay, so let's talk about well-typed substitutions. So it's the same thing we had before. So last time we had substitutions that had a parameter for what we were substituting for. We had substitutions for A's. A was just type, it was just exp. Now exp has its own parameters, right? So exp has a parameter for its typing context and its type. So our A that we're using to parameterize substitutions has to have these arguments as well, right? Things are good, we have these higher order type constructors now. But that gives us an opportunity to be more explicit about what's going on in a substitution. And when you think about a substitution, what is it doing? It's transforming a term that type checks in one typing context to another typing context. And so we can add those 2 typing contexts as additional type parameters to the substitution, and suddenly we know more of what's going on, right? So now it's not just a substitution for A's, but it's a substitution for A's that type check in G1 to A's that type check in G2. And we can see that when we create our single substitutions and in the types of our substitution operation, right? So just like I had to make the kind of A a little bit more explicit here, I had to propagate that to my class and use the same kind to talk about the kind of A in the class index, right? And so you see that most specifically here in the type of the substitution. So if we have a substitution of A's for G1 to G2, you should be thinking exp here for expressions here for A. That's going to give us an expression where the typing context of G1 of type T, and it's going to transform, it's going to leave the expression with the same type, but it's going to convert it to a new typing context, right? That's fundamentally what substitution is going to do for us. And that's fundamentally the information that we need to know to be able to make our well-typed interpreter type check, right? So if we if we go back to this slide, right, think about it here. The types are much stronger here. They're telling us a lot more about what's happening on this previous slide. So when this last line, we're promising we're going to produce a value of type T. So when we do our substitution, we better know what type of expression, and we better know we're going to end up with a closed term just so that we can do this recursive call to the evaluator. So our substitution operation has to be as strongly typed as our representation just to be able to define this function. All right, and so these are the types that we need for that. But the good news is that that was the job of the library designer. The person who's using the library just needs to write the same code that they wrote before. This is the code that we need to write, and we don't even have to write the type signatures. I just put them in for information. It's exactly the same code for our weakly typed substitution instance of this class. The same operation for substitution still works, even though we've made the types much more informative. And the best part about this particular definition is that if we got this definition of substitution wrong, we would get a lot of errors from the type checker. The type checker would tell us if we screw up the substitution in some way. Like if we forgot to apply the substitution here to apply sub, if we had a variable, this variable x is a variable from context G1. We couldn't just replace this line here with var ex, just leave it alone, because that wouldn't be a variable in context G2. The only way we can get that variable is to look it up with the apply sub operation. If we forget to do one of these recursive calls on E1 or E2, we would get a type error because the context wouldn't line up. And so the typing, these precise types are going to force it so that pretty much the only definition that's going to type check is the correct definition for us. And that's a really good thing, like especially if you're a library designer, you worked really hard to set up the types for your library. Now the types are there to help all the users of your library do exactly the right thing. Okay, so that was all, and I see that I am running a little short of time, but that was all for the simply typed lambda calculus. Now I want to switch to system F, right, and say, okay, we did it for a language that just had integer types and arrow types. What if you had binding in the types themselves, right? And so that means we have a lot more substitution, a lot more binding going on. So what if we have system F where we have polymorphic types that we need to substitute at the type level, and we also need to be able to bind at the type level, right? So in order to do that, right, I want to take my definition that I had before, my AST that I had before, and I want to extend it. So the first thing I need to do to extend it is I need to add new constructors for our new type forms, for variable types and for polymorphic types. So this is my binder for type variables. And here I'm just using the weakly typed index that we saw at the very first part of the talk, right? So this is just a weakly typed index to represent type variables. And so I want you to make sure and not confuse it with our strongly typed index that we just saw for the strongly typed expressions. So types are still going to stay weakly typed, but expressions we're going to represent our index using the strongly typed, right? So using the substitution library for the second part of the talk, right? Now, we're going to take this part right here. This is the same thing we saw before for the simply typed lambda calculus. What we want to do is we want to take the exact same thing and extend it with two more data constructors for type abstraction and for type instantiation, right? We're not going to make any other changes, right? We're going to have the same typing context, but we need to say what happens to the types when we create a type abstraction, when we generalize over a type variable, and what happens to the types of our expression when we instantiate a type variable, right? Now, in order to say that, if you remember the typing rules for system F, like there was a substitution in the typing rule itself. So we need to know how to substitute in types in order to specify the typing rules, right? So how do we define substitution? Well, we have a library for substitution. Let's use that library. So I have this new language that has a binding form that I need to be able to substitute for. So in order to have a substitution, definition of substitution for that language, all I need is an instance of the same class, of the same subsdb class that I had before. Just need to say what the variable form is for the type language. So notice here I'm doing tie because I'm defining substitution for types. And I need to say where the binder is. I am substituting the polymorphic type is a binder for type variables. And so I get the substitution operation. It just falls out for me. Now, the tricky part is that I don't need the substitution as a function I can call. I need this substitution operation in the type itself. So I need to use this function that I'm defining as a type. And normally this is where you need a dependently typed language in order to be able to take functions that you define and use them in your types. And we don't quite have that in Haskell, right? We can't take functions, normal Haskell functions, and use them to describe types. So what we have to do here is add, this is where the singletons library comes in. So the singletons library has a little bit of magic for us that where if we put our normal term definitions in some singletons brackets, it will create the exact same version except one level up in the type language that we can use for us. So we don't have to define it all over again, just so that we can use it in types as well as in terms. And in order to for this to make sense, right, notice that this is working directly with my library for substitution. So in order for this to make sense, I also have to do this, put my library itself in the same singleton brackets. But once I do all of that, then the payoff is right here, right? So if you look at the definition here for type app, right? So we want to say, when is a type application well typed? If I have an expression that has a polymorphic type, right? The result type should be substituting some argument type for variable 0 in the body of that polymorphic type. So I get to use the substitution operation that I defined on the previous slide. The only change is I have to make it a capital letter to refer to the one generated from singletons, right? Both for single sub and for subs, right? So singletons is generating for that. It's also generating this special type here, sing, that's giving me a way to represent this type argument, both using a term expression and as something that I can use to represent in the type itself. All right, so singletons gives me that, and it gives me promoted versions of these operations that I need to use in these types. Right, the same thing, we need similar things in a lambda expression, right? So if we want, for a type lambda, if we're trying to do a type abstraction, if we want to create a term that has a polymorphic type, well, the body of that polymorphic has to type check in a context where we've incremented all the type variables. And I haven't really said what this inklist operation is. It's another very simple operation that I've defined via the singletons library. Okay, so last bit, and this is where this last dragon comes in. So I said there's no fairy tale ending. We kind of get a little stuck here, and I need to show you how I got unstuck, right? So one thing we have to define when we do this is an operation for substituting types inside terms, right? And the type gets a little hairy for this operation. We're taking a substitution for types. We have an expression, and we want to produce a new expression where we've mapped that substitution across the context and applied that substitution to the type of the term. And I'm not going to go through all the details, but I will say that when we get to the lambda case, we're going to get this type error from Haskell. Right? We're going to get this type error from Haskell that says, I can't make these two contexts line up, right? This expression doesn't match that expression. And this is actually not surprising that we have this type error, right? So here I've just zoomed in on the type error really fast, right? So here's the type error. These two expressions don't line up. But this is exactly in the Coq version where they had to write a proof, right? But we're in Haskell. We can't write a proof. So what do we do? Since Freya says, what do we do? What do we do? We don't have a proof theory. Haskell's not a proof assistant. Are we stuck, right? How do we make this term type check, right? Is this the end for our strongly typed term representation of system F, right? We can't really do it. Sometimes you can convince Haskell's type class solver to do simple proofs for you. This is not a simple proof. You can't do that. Sometimes we could do a check at runtime to defer a check. We can't do that, right? The only thing I can really do here is actually tell Haskell, trust me, I know what I'm doing. Do an unsafe course of the type. Believe me, these two types are equal to these two expressions are equal to each other. How do I know that? I know it because, well, I read this paper. They proved it in Coq. I could also test it, but really fundamentally, you have to believe me. This is dangerous. I'm telling you right now, don't do this. It's dangerous if you get it wrong, Haskell seg faults, but it's exactly the right thing you need right now in order to finish this thing, right? We don't have this proof theory, so we have to have some way. And this is a trade-off, right? There's a little bit of danger, but then you get everywhere else that's carefully marked, but then everywhere else you get the benefit of these strong types. So here's where I'm going to end with my conclusions, right? So that's where we are at the limit, right? Sometimes things work. We actually weren't too surprised because it was in the abstract of the paper about Coq that they had to do the proof at that point, right? So we didn't need proofs in the first part, but we did need a proof once we got to things where we were really doing some crazy stuff with our types, right? So it's really important to think about these trade-offs. I think sometimes maybe an unsafe course might be justified here. Don't kill me. But I think it is an example of something, a discussion that we can have. But overall, notice that the types didn't interfere in any other part of our development, right? They didn't get in the way of creating our general purpose library. And in parts that I don't really have time to talk about, you can also optimize this representation so that you can actually make it efficient as well, so that your substitution and the types don't get in the way at all there either. Okay, so I'm going to end there and remind you, all of the code is available on my GitHub page. If you want to take a closer look, I have a lot more explanations of things I had to go through kind of quickly here. Thank you.